So, morning everyone. Today we have Chethan Krishnan from IISc Bangalore. Before we begin the talk, let me say a few words about Kerala Theoretical Physics Initiative. Basically, uh, yeah, Kerala Theoretical Physics Initiative is actually, I think I can feel the echo, right?
So should I wear headphones? Is it better or
No, that
maybe I
is
think the echoes are probably because multiple microphones are on. So maybe once I start, it might go away. Who knows?
yeah, maybe you can mute now.
Yeah, I'll just mute mine for a second. Sorry.
Mhm. Should I mute from myself? Yeah, fine. Okay. So yeah, what I was saying that the Kerala Theoretical Physics Initiative or KTPI is actually a collective of active researchers across the globe and who are originally from Kerala actually. So our mission is to motivate students in Kerala, students in Kerala to pursue research in theoretical physics. So we usually conduct this type of seminars and workshops in mostly in Kerala, and also we mm, uh, do active research training. That is particularly for master's students. We offer, the master's project, and we train them, and then we motivate them to do PhD in theoretical physics. So through these programs, we aim to make a very vibrant research community in Kerala. That's our hope. That's our aim. Okay, so that's about Kerala Theoretical Physics Initiative. So today we have Professor Chethan Krishnan from IISc Bangalore. So Chethan received his PhD in theoretical high energy physics from University of Texas. He did postdocs at the Solvay Institute in Brussels and at CISA in Tusti, Italy, that is in Italy. And he is currently a faculty member at the Center for High Energy Physics at IISc Bangalore. Actually, his research interests are very broad, as I see from his publications. He works on string theory, holography, cosmology, and more. So, Chetan, thank you very much for accepting our invitation. And today we are going to talk about the arrow of time. So, you can start, Chetan. So, as you said, I want to tell to the audience that you can unmute yourself whenever you have questions or confusion. You can unmute yourself and ask questions in between the talk. You can interrupt Chetan and ask questions. You don't need to write in the chat. So, yeah, you can start, Chetan. Thank you.
Okay. So can you hear me? I have my fan on, so maybe
Yes.
there is. Is it okay? Can you
That
hear
is
me?
fine. That is fine. That is fine. Yeah.
Okay, great. So let me make the whole thing full screen. Yeah. So as Ratul, I think it was Ratul who was speaking, right?
Yes. Yes. I am grateful. Yes.
Yeah. So as Ratul was saying, like please feel free to interrupt me at any time because I don't have to necessarily get to the end of the talk. And also one more thing I wanted to say, since this is KTPI seems like an effort to kind of um, so encourage research in like Kerala. And, so I really think it is very possible for, even if you are working in what you consider to be a small university, I mean, increasingly in the last 20, 30, 40 years, like, the knowledge landscape has been becoming more and more flat in the sense that, when, for instance, you hear about the previous generation of Indian scientists, for instance, there was definitely a polarization of research potential or research possibility in the West, because essentially you need some kind of a community or some way of interacting with research, cutting edge research on a regular basis, especially in theoretical physics. So, and I think it became really possible in India or in more globally ever since the internet came out and archive came up in 1991. And that has really made everything quite, we really have access to knowledge and current research in a way that we never had before. So, and that's one reason why science in India has been exploding, or theoretical physics especially, because experimental science always requires infrastructure and money and so on. But theoretical physics, you only need human capital at the end of the day. So which means that it is quite, in some ways, we can just do what, as long as we have access to the correct information. And I think that this has become even more so now that ChatGPT is there. I don't know whether ChatGPT will overtake humans and then we don't have anything to do in science. That is yet not clear. But at this present moment, there is a massive opportunity, which is that you basically have access to, you don't have to talk to some of the big shots in order to figure out what the current status of knowledge is in any specific cutting edge of thing. You can actually ask ChatGPT. I mean, that's like a remarkable, it's even more of an equalizer than the archive was and the internet was. And I think that it is really possible, and it's really like your own mental limitations, or like your own like mental blocks are what is holding you back. And I think it is really possible for very local places to really do research, as long as you have the ambition. Of course, it takes hard work and ambition, there is no question about it, but it's only that, right? That's something fundamentally that, at least in principle, we have access to. So I just wanted to start by saying that, because the whole purpose of this is in some sense to encourage research from places which are not historically necessarily associated with research. All right, so that's what I'll say in the way of general gyan. But so the topic. So I was asked to give a talk on to this KTPI, and I'm not exactly sure what exactly the level at which I should pitch it. So my current research is mostly on black holes, and this is something that I had kind of sort of glancingly thought about a few years ago, and maybe around during COVID time. When you're thinking about things which are not really a standard thing that you often think about. So I was kind of starting to think a little bit about it, but I had some ideas, but I didn't really develop them. So I thought that since the talk was supposed to be at the colloquium level, it might be a good idea to kind of, think about it sort of afresh. And that's one reason why I decided to give a talk on this. So, and at the very end, there is hardly anything original here. All of it is like well-known stuff, basically from the time of Boltzmann. But there is like some potential line of thinking that I kind of would like to develop. And if any of you want to think about it, you can also think about it. May not be, I'm not saying that the question is still not sufficiently well posed to actually form a research problem, but at least it's a direction that I think might be promising. Okay, so that's where I will leave the talk. So as I said again, like, please feel free to interrupt me at any time. And, if you cannot hear me, so yeah, I mean, you guys can still hear me, right?
Yes, sir. Yes.
Yeah, very good. So, yeah, I mean, my number is 8197. I mean, okay, anyway, so if I get disconnected, I will not know. That's my only concern, because, the thing is, yeah, okay, so let's just hope that nothing goes wrong. So you can email me. My phone is with me. So in case some disconnection happens, it happened once. So, okay.
So maybe, yeah, I can email you. You're accessible.
Yeah, you can email me. You can email me on the same email, and I'll, I will keep the alerts on. So I think it should be
fine. Fine. Okay.
So, okay. So let's start with the title of the topic, the arrow of time. And so the slide is moving. So basically what I'm going to talk about, there's an obvious fact about nature, which is that, the future looks different from the past. This is something that we know very well. It's experientially an obvious fact. And, the often cited example is that of, let's say, a glass of water falling from a table and breaking into thousands of pieces, hundreds of pieces. And that is something that we see in nature all the time, or at least it is something we can imagine. But even though it might not seem like it, the laws of nature are perfectly consistent if the glass was, the broken shards of glass assembled together and climbed back onto the table. That's a perfectly allowed solution of Newton's laws, if you like. Okay, so the reason is, it's just that you just reverse the velocities of all the particles, then precisely the same trajectory will be traced back. But it's something that doesn't seem to happen in nature. And so this is sort of the most obvious way of motivating this distinction between past and future that we often see. So another and more striking and important thing is that we remember the past, but we feel the future is yet to unfold, right? I mean, so there is a sense in which we feel that the past is something that has already happened and it's somehow immutable. But we seem to feel like we have some form of agency in controlling what happens in the future. So but again, this is very puzzling from the point of view of the laws of physics, including quantum mechanics, which is basically the statement that the equations of motion in physics are deterministic equations. I mean, you can talk about interpretations in terms of probabilities and so on, but that doesn't change the fact that the equations of motion, like for instance, Schrodinger's equation, is a perfectly deterministic time evolution equation. Okay, so it is not clear why is it that the past feels fixed and the future feels free. So so this is in a universe governed by deterministic equations, in case all fundamental laws, this is true for all fundamental laws of nature. People oftentimes bring in quantum mechanics to talk about it, but quantum mechanics doesn't really help you there, because the basic equation of quantum mechanics, which is Schrodinger's equation or Heisenberg's equation of motion, if you think in terms of operators, both of them are deterministic equations. They're just ordinary differential equations for operators or functions or whatever, but they're just ordinary differential equations. The interpretation might have probabilistic aspects in them, but it is not the case that the wave function at a later time is entirely fixed if you know the wave function at an earlier time. Okay, so that's the sense in which the universe is deterministic. So, so making sense of this apparent asymmetry between future and past in a world where the laws of nature are deterministic is basically the basic problem of the arrow of time. Okay, so it's not obvious yet from what I said that there is actually a contradiction, as we will see. But it is clearly, we will finally conclude that there is, if not a contradiction, there is at least something that we are missing in our understanding of how the past is distinct from the future. So there are also closely related but distinct questions in cosmology. And we have a huge amount of evidence that the universe started out from a very hot and dense state that we call the Big Bang, which is in our past, right? And the universe seems headed towards ever-increasing expansion. And with some minor assumptions, we don't understand everything. Universe, the data from the universe is hard to extract because, like everything, all the things that happened back in the day are like many, 13 billion light years away. So it's hard to extract. There is not it's not yet quite a data-driven subject as many cosmologists like to pretend. So we don't have as much information as we would like. So it's hard to precisely pin down the model in which that explains our universe. And there are other problems as well. But modulo some minor caveats, it is natural that the universe will evolve. The future of the universe looks very distinct from the past of the universe. So this is let's say one way in which the universe, this is also sometimes called the arrow of time problem, which is slightly different because the previous one that I said is basically a statement about the laws of physics itself, or how the universe reflects the laws of physics. But here it's a statement about how the past is distinct from the future for the entire universe. Is there what happens there? Okay, considering the stark asymmetry between future and past, one might expect that the fundamental underlying time evolution laws of physics must have some kind of built-in time asymmetry in them. So I'm kind of recapping what I already said, but turns out that this is not the case. So how can the physics around us be so essentially and fundamentally time irreversible if the laws of nature have no time asymmetry in them? And this is what we would like. So this is what we want to I will explore this a bit, and then I will tell you why this is not quite a contradiction. You might think that this is actually a contradiction because, you might think that, if the laws of nature are time reversal invariant and the universe is not time reversal invariant, and clearly there is something wrong with what we are saying, right? But that is not quite the case, as I will argue. The laws of nature can be time reversal invariant, but at the same time, the universe can be distinct in the past and the future. So as we will see. So, but again, as I said, that is not quite, it's one thing to not have a contradiction and one thing to understand why that is the case. Okay, so those two things will play a role in our story. Okay, so let's consider the first candidate of a fundamental dynamical law of nature. So, or at least something that, initially we believed was a fundamental law of nature. And it has many of the properties of the actual fundamental laws that we believe, like, Schrodinger's equation and so on. So Newton's second law is basically, I'm writing it as in this form where f of x is some field, and I'm only writing one coordinate, but none of these things matter so much. You can make it very easily into a three-dimensional problem and all that. So the basic equation of physics, like in classical mechanics, is Newton's law, and you immediately see that because the equations are second derivative, t going to minus t is actually a symmetry of the system. So it's not crucial that the equations are second order so that this irreversibility holds. Even for first order equations like Schrodinger equations, it's just that you need to find a sign reversal of the various ingredients in the equation so that the equation remains invariant. That's all you really need in order for the equations to be time reversal invariant. So, but here it's very easy because it's a second derivative. So which means that t going to minus e, the equation doesn't change at all. So you don't have to do anything else. But even for first order equations, in many cases, you will see that time reversal is in fact a symmetry. When as t goes to minus t, you can change other things in the equation to ensure that the equation remains invariant. Okay. So any questions on that? So this is my first equation. Any question, comment, thoughts on this? So am I going too fast? Am I going too slow? I mean, I have a tendency to speak fast. So then I find that I'm kind of like, so if you have questions.
This is fine, Chethan.
Yeah, okay. Great.
This is fine. I mean, this is fine.
Yeah, okay. Good. So, so what we have established is that Newton's second law is an example of a basic law of nature that is time reversal invariant, or sometimes it's written as T invariant. Okay, so you can, so if a differential equation is time reversal invariant, it has a very remarkable property. For any solution of such a differential equation, its time reverse is also a solution of the differential equation. Okay, so if you notice, you must have seen examples of this when you're solving Newton's laws in high school and so on. So let me give you an example of what I mean. It's that let's say we drop a ball from the top of a building and it reaches the bottom of the building with a velocity of some velocity. Okay, so what it means to say that Newton's laws guarantee the existence of the reverse solution is that if you launch a ball from the bottom with some velocity, which is the opposite of what it landed with, if you reverse the time essentially, or reverse the velocity here, it will reach the top of the building and it will basically retrace the path that it took. Okay, so this is kind of an obvious fact that we don't even really notice when we are talking about Newton's laws, but this is what it really means at the fundamental level is this statement. Okay, so if whenever an equation has a symmetry, or maybe let me because specialize to the case of time reversal. So if you have a time reversals as a symmetry in a theory, the time reversed equations, time reversed solutions are also solutions of the equations of motion. Okay, so this might seem like a very trivial fact, but it is actually quite remarkably powerful when you change this from to other symmetries, for example. So for instance, it is a general statement about symmetries of differential equations in general. So whenever there is a differential equation and it has a symmetry, you can argue that the solution, you start with the solution and you symmetry transform the solution. The solution that you get, the new solution that you get, is also a solution of the differential equation. Okay, and this is very closely related to, for instance, things like symmetry breaking and Higgs mechanism, etc., in the standard model. So even though here it is a very pedestrian and sort of almost mundane fact, I want to emphasize that it is a very crucial aspect of the laws of nature in general. So there are many other equations in physics which also have this property that the symmetry of an equations of motion, symmetry of a differential equation is realized in the space of solutions of that theory. Okay, so that's another way to say the same thing. And it's a simple illustration in the case of this particular discrete symmetry, which is time reversal. That's what we are seeing here. Okay, so what that means, and this is the reason why in my first slide I mentioned that, like, the idea of a broken pieces of glass assembling together and lifting itself up to the table is sufficiently it's we don't see that at all in nature. So you might even suspect that that's not allowed by the laws of nature, but it is allowed by the laws of nature, because what you're really doing is that you're simply reversing the initial, the final state of the final velocities of all the particles or all the shards of glass or water or whatever. You reverse all the velocities, and if, let's say, Newton's laws are the laws that govern it, then it should assemble together and rise up and sit on the table. So that's why it is actually a contradiction, or it's at least a puzzle. Okay, so yeah, so this is the simple example that I gave of why this is true. And so what does this mean? So this means that Newton's law alone cannot tell us why we never see a broken glass and spilled water assembling themselves into a glass of water on the table. Okay, so even though it seemed like a very mundane fact, it already tells us that the way we see nature, right? We cannot look for an understanding of the time reversibility or time irreversibility that we find in nature in the equations of motion, because both forward solutions and backward solutions are perfectly acceptable solutions of Newton's laws. Okay, so we cannot find a resolution to this time reversal puzzle. The fact that the universe is seems to distinguish between the past and the future is not, we cannot look for its solution in the equations of motion, because the equations of motion allow both. So that's what we just from this very simple and basic observation, we see that. And according to Newton's second law, if we were to precisely reverse the velocities of every particle, we should in fact be able to produce a self-assembling glass of water. So in order to understand why this reverse configuration never happens in our experience, we need something more. That's sort of the punchline. Okay. So again, at any point, if you have any questions, please stop me. So there are not many equations in the talk, but I think that we will get slightly more abstract as we go. So it behooves you to ask questions when necessary. So, and I think it is anyway. So some amount of courage in stopping, and like when somebody is going on blathering on like this, you have to have the courage to stop me at some point anyway. So I think that's a good thing. So okay, so
Chethan,
yes, yeah,
I have a question. So
yeah.
actually, so are you saying that this is something we need to add more equations, or do we need to add more
So
forces?
I'll come to that. I will come to that. So I mean, see, once you have the equations of motion, like essentially we believe that we understand the laws of nature. So the distinction will actually be that there is a distinction between initial conditions and final conditions. So what kind of initial conditions are allowed is something that that the equations of motion or the laws of nature don't really say anything about. That's basically
okay. So we assume that we know all the laws of nature.
Yeah. So there's
all the information about
Go on.
Okay, so we are assuming that all the laws of nature we know, and all the information about the states we know, right?
We are not assuming necessarily that. We are just saying that if the laws of nature have time reversal invariance, then which seems to be the case, right? I mean, so I'll argue that like with some slight refinements, essentially the same statement is true even at the level of the standard model or general relativity or various things like that. Okay. So in various, with some notion of it's you could argue this at various levels of generality, but let's take the standard model. That's, I think, a concrete example. So there you can argue that there exists a reversal symmetry which is respected by the standard model, which should make which means that the forward process and backward process are equally probable. Okay, or they have the same. So there is some notion of time reversal invariance, let's say in the standard model of particle physics. Okay, so our working horse for a theory of low energy physics, if you ignore gravity. Okay, everything is there. So, but the problem is that even with forward and backward, so that means that we cannot look for a resolution of this time asymmetry that we see in nature in the standard model. Standard model equations of motion do not have anything to say about it. Both forward and backward are fine. So we will have to find it elsewhere. And what I'm going to say is that it is related to the choice of initial conditions, and initial conditions are a separate bit of data on top of the equations of motion. And that initial condition is where the real puzzle lies. So that's what I will argue in a second.
Yeah, I understand. But my confusion was, suppose we combine all the laws. Like here it is a Newton's law, but in the case of a falling glass, we may need more like electromagnetic.
So for instance,
and other kind of theory.
That's right. So electromagnetism is also part of the standard model, right? So,
So suppose we combine all
everything we know, if we so all the things we know have that time reversal invariant.
Yes. And suppose we combine everything, then do we expect that the time reversal is still at
it is always possible that it may not be part of the fundamental laws of nature. It's always possible. You know what I'm saying? We don't really know. But the problem is that everything we know seems to suggest that the equations of motion have that time reversal invariance, some form of time reversal invariance. But at the same time, then I think there are only two options in front of us. One is we have to look for either some other mechanism where we can find the origin of the time asymmetry. If we cannot find it, then we have a contradiction. Or we have to count on the fact that there is some new law of nature where time reversal is somehow implicitly broken, and we have no paradigm for it. Okay, but luckily the point is that because initial conditions are also part of the description of the system, we are not quite at the level of a contradiction, because we can find the resolution of time asymmetry, because equations of motion alone does not describe nature, but we also know the initial conditions and so on. So, and if initial conditions satisfy certain properties, as we will see, time reversal invariance can be broken. So it is what is called a spontaneous breaking of time reversal rather than an explicit breaking of time reversal. So spontaneous breaking basically means that the solution that we are looking at, the explicit solution that we are working with, is not a time reversal invariant solution. Okay, but the solution so as opposed to, let's say, the equations themselves, the equations of motion themselves, like Newton's laws or quantum mechanics or standard model, or with minor caveats, even general relativity, is invariant under time reversal. But at the same time, because the initial conditions are sufficiently have this freedom, we will basically find that they are not this thing. So that's sort of the answer. Is that good enough for now?
Yes.
Okay, good. So you have one more question? Yes, please. Yeah.
So is it saying something like if we choose one way is forward, then another way is obviously reverse, and we can switch between forward and reverse comfortably?
The equation, the solution, both solutions exist. Whether we can switch between one of them is not really, like you will have to reverse every motion in the world, right? So that's not something oftentimes up to us. But in local experiments, etc., we certainly can.
Okay, so it's up to the person who do the calculation to choose which initial conditions are
right. I think that, like, both. So Newton's laws, let's say that we are describing Newton's laws for a set of particles or whatever. So then you can have initial conditions that you choose. So every possible solution which is in the forward direction, you can construct explicitly the reverse solution by just reversing the velocities. That's it. So you can always do that. So at the level of so that means that that's an allowed configuration in nature. Whether it is explicitly realized in nature is a different question, and we don't see that. That's the puzzle.
Yeah. So, one more question. So you mentioned about this spontaneous braking and something like explicit braking. If I add something like a friction or some dissipation force into
that will be an explicit braking.
Okay.
That will be an explicit braking. But note that there are no genuinely time reversal braking forces in nature. Friction is basically an approximation for all the electromagnetic interactions between some surface and the particle that is moving there. But if you really had a fundamental theory like we have in the standard model, then you also have to model the particles that the floor is made of. And in that situation, there is no genuine dissipation. So if you really look at a fundamental theory, all forces are conservative. And that's thanks for asking that question, because one might worry that, so if you look at a genuinely fundamental theory, and you have what the genuinely fundamental theory gives you is a bookkeeping device for where all the the energy of the ball that is rolling on the floor went. So it is telling you that it went into some particles, and if you had infinite control, infinite power to compute and so on, then you will actually be able to see that the process is actually genuinely reversible. But it is just that because it's like there's a huge collection of particles, etc., it's getting lost into this thing. And that is the kind of thing that I will make precise in terms of initial conditions in a few slides.
Okay, thank you.
Okay. Yeah.
Thanks.
So yeah, before we go there, let me also just mention one more thing, which is that somehow you may think that time reversal invariance is just an artifact of classical physics, because that's the setting in which we, Newton's laws we discussed. Maybe there is time asymmetry in maybe quantum mechanics or relativity or something like that. But that hope is immediately dashed. And it's not, I mean, I don't know whether it is a good thing that it would have been like that, but at least that doesn't happen. Because the dynamical equations arising from quantum mechanics and relativity are also time reversal invariant if you define time reversal invariance suitably. Okay, so and that's what I mean by there's a minor caveat here. So if if you're not familiar with some particle physics type of stuff, you can ignore it. But the point is that in quantum field theory, which is basically our basic theory for, let's say, constructing things like the standard model of particle physics, T invariance is replaced by something called CPT invariance. And CPT invariance is always there in every model of particle physics. It's necessarily there. You can prove that it should exist in any quantum field theory. And So which is essentially a stand-in for this time reversal invariance. And that's sort of the point. So in some sense, some version of time invariance, which we call CPT invariance in quantum field theory, is there even in our most fundamental description of particle physics. Okay. So general relativity is a bit more subtle for some reasons, which is a general relativity time is kind of like it's a coordinate choice. But in any particular solution that you can write down, the time reverse solution that you can write down is also a solution. So there again, it is not like the interpretation of time is a little bit more fuzzy in general relativity, but at the same time, to the extent that is well defined, it's still valid. The time reversal invariance is still valid. So yeah. So for instance, you might, let's say you take a black hole that is rotating in some direction, which is a solution of general relativity. The rotation in the other direction is also an acceptable solution of general relativity. Okay, so that is the sense in which I mean it. But general relativity, there are some conceptual issues related to, we don't fully understand the nature of time in general relativity. So, but to the extent that we understand it, it seems like some version of time reversal invariance is still true. Okay, so what is this extra? Yeah. Was it a question?
Chethan, yeah. So I was just asking if CPT is tight in the fundamental level, why are we looking for a breaking of time reversal at the fundamental level? Do we need at the fundamental?
You're not looking for a. So at the moment, I'm not looking for a breaking of time reversal invariance, like at the fundamental, not an explicit breaking. I'm basically like my question will be about the initial conditions do seem to distinguish between past and future. So that's what we are really. That's the real puzzle of. So the way, at least, let's be conservative. It's generally speaking, I think that if you're not conservative in physics, then I think, like it is, you can do whatever, but it's also not very tight. So you should be as radical, as conservative as possible, and as radical as you're forced to be. So this is, I think, where you generally find the good boundary between decent research. Like for instance, like you can make things, you can speculate by making the fundamental laws themselves time reversal time reversal breaking, but that's not what we find in all the examples we know. And so then once you make it, but I have a suspicion that might actually be true at a very fundamental level. I don't know. Okay, so that's a different question. So, but at least it's a possibility. I'm not ruling out that possibility. But what we are going to talk about is that let's assume the more conservative scenario, which is that time reversal invariance is actually realized in nature at the level of the equations of motion. And then we immediately get to the point where we need to understand the story becomes a story or a question of understanding initial conditions versus final conditions, as we will see in a second.
Okay.
Yeah. So the key point, we have not been paying attention to this question, as I said, is initial conditions. And to describe evolution by solving a differential equation, we need to specify initial conditions. And while the T invariants of Newton's law guarantee that the time reverse solution is also an acceptable solution, there is no requirement that the initial conditions corresponding to such time reverse solutions will actually show up in nature. Okay, so this is an important statement. There's a qualitative statement, and it's I don't think it is. You just have to sort of understand the statement, what I mean there, which is that initial conditions of any kind are allowed in the space of solutions of Newton's laws, but which of those initial conditions actually show up in nature is something that only nature knows. We have no control on it. We don't have a theory of initial conditions. We only have equations for our laws of nature, and the initial conditions, as we understand it in every theory that we have at the moment, initial conditions are just God gives them or nature gives them or whatever. So that's where we are. So in other words, glasses with water appear routinely on tables as initial conditions. Let me just finish this one sentence, one slide, and then I'll take your question. So in other words, the glasses with water appear on tables, routinely appear in our neck of the universe, like we find them. But like we don't find configurations where shards of glasses are distributed out, but their velocities are precisely aligned so that they can combine and form, combine and form a glass of water and arrange itself on a table. Okay, go ahead, please.
Yeah, my doubt is that maybe it's because I didn't understand well. So maybe some initial condition of some process can be described as a final state of some other position, right? Some other process, right?
That's right. Yeah. So all of those initial conditions, both initial conditions and final. So the choice between the difference between initial conditions and final conditions is really, we are the ones who are deciding it. Like you could have final conditions and you put that as, you could start your equations of motion with those final conditions, and then you could evolve them, evolve them backward, and then you will find the same, like just as I said, I think it is a good example is to keep in mind the ball being dropped versus the ball being launched from the ground. So what you are doing is you have an initial condition. So of course, like, you start with an initial condition, which corresponds to a ball being dropped or thrown or something from the ground, from the top. And you take that final condition that you find at the bottom and reverse the velocity. It will precisely retrace the path.
Yeah. So is it safe to say that in nature, the choice of initial conditions in nature is have some kind of statistics that mostly likely to be only happen, something like that?
I think you can ask the question maybe after I say a few more things, because I think it is going towards something similar. But yeah, I mean, maybe you can ask the question. Maybe I think I will address something of the kind. It is, see, it's a question of, yeah, I mean, I think that your question is kind of on the right track, but making it precise is really the challenge. And it was, in some level, it was done by Boltzmann. So I think you can, if I don't address your question maybe in the next 3 or 4 slides, you ask me again, then we'll see what happens.
Okay, thank you.
Yeah, so yeah, why is this so? What is special about certain initial conditions as opposed to others? And the second question is, so there are 2 questions here, okay? Why is it that, so why is it that certain initial conditions seem more common? Okay, the glass with water sitting on a table, appears as a more natural, more common initial conditions, while the one with the broken shards with precisely engineered initial conditions for the velocities does not seem to happen. So we will answer the second question first. Okay, why is it that some questions appear, some initial conditions appear versus some other initial conditions? We don't have a really good answer. And that is what will become the challenge. That is what we will discuss towards the end. But what is special about certain initial conditions opposed to others, we can explain. Okay, so that's what we will do. So the tables, the glass sitting on the table, what is special about those initial conditions as opposed to the one where it is broken and the velocities are precisely engineered? So that distinction we will be able to make. Okay, but we will not be able to explain why is it that the glass sitting on the table is the common initial condition that we find in nature. Okay, so as I said, even though the talk is not very mathematical, we are getting into slightly abstract territory now. So if you have questions, please feel free to ask. So the distinction I'm making is a very conceptual one, which is that there exist certain initial conditions which are very common in nature, and there exist other initial conditions which are less common in nature, or at least, like we find that certain initial conditions which seem natural in our case, and there exist other initial conditions which don't seem to as much. So the velocity reversed broken glass initial condition, we never find it. We essentially never find it in nature. So, but on the other hand, the one that where the glass is sitting at the top, we do find it. Okay, so the distinction between these 2 initial conditions and what makes one special as opposed to the other, we will be able to explain. But why one is more common than the other, we will not be able to explain. So that's the point I'm trying to make. Okay, so yeah, so if you have any questions, again, please feel free to stop. I don't have to get to the end of the talk, even though there is one open question at the end, which you may, may be interesting. I don't know. So, okay, so the question of what is special about some initial conditions as opposed to others was first addressed with the full gravitas it deserves by Boltzmann. Okay, Boltzmann was primarily interested in understanding the second law of thermodynamics back in the day. And our question is fundamentally a question of the second law of thermodynamics. The second law of thermodynamics essentially says that, disorder increases, entropy increases, and so on, as you're quite familiar. And we will actually talk about it. So, so he wanted to have like a mechanical explanation for the second law of thermodynamics. So Boltzmann was like, one of the big geniuses of physics. So what he wanted to explain was he wanted to explain things in terms of atoms, which was a general placeholder name for all small particles, molecules, whatever, back in the day. And he wanted to explain the second law of thermodynamics in terms of the Newtonian mechanics, essentially, of these small particles. And Boltzmann believed that if one knew the basic dynamical equations, let's call them Newton's laws, then by applying it to systems containing large collections of microscopic particles, large collections of microscopic particles, one should be able to reproduce macroscopic phenomena. Macroscopic phenomena means like, like things involving gases and water and gases and so on and so forth. Anything that is macroscopic, anything that is our scale or bigger. So this is the philosophy underlying statistical mechanics. Statistical mechanics is a branch of science, as you know, which basically whose stated goal is precisely this. Okay. So the challenge for Boltzmann was that he could explain gas laws and this thing and so on, even before him, Boyle's law, this, that, etc. But nobody seemed to have a really compelling answer for why is it that the second law of thermodynamics holds? Why is it that, things seem to be evolving towards disorder, like the glass of water that I was talking about, but not in the other direction? So let me make a quick historical aside, because it's sort of a personal tragic story, but at the same time, an interesting, the structure of scientific revolutions, how they works. So even though the statistical mechanics are a key piece in our understanding of physics nowadays, Boltzmann's belief in atoms was very harshly criticized by many people, especially Mach and Oswald and some other people. And their severe criticisms affected Boltzmann so much. And he was called basically a metaphysicist, in the sense that, atoms, nobody could detect them. I mean, this is some sort of speculative nonsense. And this is a criticism that even theoretical physics now face, which is that, like whenever you come up with a thing that you cannot immediately test, the challenge is always to explain the observations that you see. And of course, at the time, people believe that atoms are just a metaphysical fiction. It has nothing to do with nature. And so Boltzmann basically killed himself while he was in Trieste. I've actually been to the place where, the place near Trieste where Boltzmann killed himself as sort of like a scientific pilgrimage. What was it? Yeah. So, and a year prior to Boltzmann, what is interesting about the story is that the discovery of atoms essentially began even already a year before Boltzmann's death. And Einstein, basically, I think in 1905, he had a paper in his miraculous year. Einstein had a paper on the Brownian motion, which essentially showed the existence of, he showed indirect evidence for the existence of atoms by demonstrating Brownian motion as a phenomenological consequence of atomic structure. Okay, so, and it became so, but Boltzmann apparently, like back in the day, there was no archive, and I think Boltzmann did not know about it. So I think it took, even after 1 year, in 1905, the paper came out, but 1906, he still didn't know it, I think. And he was getting, hopeless, and he finally killed himself. I mean, partly because of that, probably maybe he was a depressive person to begin with, who knows. So whatever it is a tragic story. And what happens is that in the next decade or so, the evidence for atoms became so profound that within a decade of Boltzmann's death, we accepted atomic theory, even though it took us, maybe another 60, 70 years to actually discover, like use scanning tunneling microscopes and so on to take pictures of atoms. So the evidence for atoms was so overwhelming within a decade after Boltzmann's death that, but interestingly enough, like you change ideas only as people, generations change. Ostwald changed his mind when the evidence piled up, but Mach never changed his mind, and he went to his grave thinking that the atomic hypothesis was wrong. So there's an interesting sideline, and the ideas, the arrow of time and entropy are such profoundly important ideas that cuts across all branches of physics, and such revolutions always have to be like, they involve some struggle. Okay, so so this is what essentially Boltzmann's primary, he did many things, but one of his most important contributions was this definition of a quantity called entropy. So that's, so this is what makes this so difficult at some level, because atoms are not observable. Entropy is a hard to define quantity. What exactly is entropy? I mean, you can think about energy, you can think about force, all of those things make some sense, but what is entropy? It's not an observable, So a quantity called entropy was introduced as a useful thermodynamic variable to describe the second law by Clausius long before Boltzmann. And the usefulness of this quantity was that entropy never decreases in the macroscopic processes that occur in nature. So essentially, entropy functions as a way to define thermodynamics. So second law of thermodynamics. In fact, one could view the arrow of time as the direction of time at which entropy increases. So entropy basically gives you this sort of an abstract definition of an object, which gives you a qualification or a characterization of the arrow of time. Okay, so what we will try to say is a few words about what exactly entropy is. And Boltzmann understood that to get an understanding of an arrow of time, one would have to come up with a microscopic, that is statistical mechanical definition of entropy. And he believed correctly that one needs to understand a mechanism behind the second law. Okay, so to get a sense of what he had in mind, we can think about temperature. So because temperature, you know, is in statistical mechanics is viewed as the average kinetic energy of particles. So average kinetic energy of particles, every particle has at a microscopic level some kinetic energy, but that kinetic energy when averaged over all the particles roughly gives you a measure of the temperature of the system, and it turns out to be useful as a macroscopic quantity. Okay, so it's a measure of the energy content in the system. So this is the kind of thing that he wanted to understand. So again, if I'm going fast, you can stop me. I mean, I don't know how much time is the talk. Is it 1 hour or so? I think I'm not yet at the place where it is sort of interesting yet. So how much is the time of the talk?
It is 1 hour, but that is fine. It is not a strict time.
Okay, so maybe
schedule.
I'll take like 10 or 15 minutes more, and I think I'll be able to.
That is fine. Yeah, that is fine.
Okay. So yeah, Boltzmann defined entropy as a measure of the number of different microscopic ways in which the macroscopic configuration can be realized. Okay. So this is some equation. You don't have to really pay attention to it. Just the idea is sufficient, which is basically that it's a characterization of the number of microscopic ways in which a macroscopic system can be realized. For instance, if you have a room full of gas, you can specify it using, you don't have to specify the velocity and temperature, velocity and momenta, velocity and position of every particle in this room in order to specify the general, volume, temperature, pressure, the macroscopic quantities associated with it. Because there will be many configurations which will all correspond to the same macroscopic configuration. Okay. So entropy is a number of microstates that correspond to the same macro state. So then how many number of microstates can realize this thing? So a configuration has high entropy if there is a huge number of microstates which realize that macro state. Yeah, I think this is the example I gave you. So let me just go ahead. Yeah, so for instance, if you have to confine all the gas molecules in this room to one corner of the room, that's a low entropy configuration, because the moment you take out some way of preventing it from, so the moment you remove the box that contains the air molecules, it will spread out everywhere, because the macro state which has higher entropy is the one where the air is distributed everywhere. Okay, so that's sort of intuitive, and that's the main message here. So at least, yeah, please.
Can we say that the maximal entropic state is the maximum stable state?
Maximum entropic state
maximum stable state.
Yeah, so there is a notion of global thermodynamic equilibrium. Okay, so so if I specify, let's say, like if you have in this room, for instance, if I specify the total energy, like it's a closed container or closed room, and if I specify the total energy of the room the total energy of the particles in this room, then no matter where I initially start with, let's say the particles are all in some corner or they have some very specific velocities or whatever, but at the end, as you wait long enough, it will wait and you don't have to even wait long enough. It is, it's a fairly mesoscopic time under which the room will reach a configuration with maximum global thermodynamic equilibrium corresponding to that particular energy. It is sometimes called the definition of the microcanonical ensemble. So microcanonical ensemble is basically the global configuration. There are many microscopic configurations that are allowed, but they all correspond to the same global energy and the number of particles that are given, etc. So what you're calling stable is basically the global thermodynamic equilibrium state. So once you are there, then there is, at least at the macroscopic level, there is no evolution, because you are in a except for maybe fluctuations and so on, which is like the time scales of those are like much bigger than the lifetime of the universe and so on. So that is what one means by stable here. So yeah, does that answer your question?
Yes.
Yeah, okay. So if you so I think I gave this example already. So most states, so basically the systems have a tendency to move towards, so there are much more configurations available where the entropy is higher, okay, by definition, essentially. So which means that if you start with an initial state at a lower entropy, it is natural for a system to evolve to higher entropy. Okay, and this is how Boltzmann understands the second law. The latter microstate has higher entropy according to Boltzmann, the one where the gas, is not localized in some corner of the room, but everywhere. And because of which, almost all initial conditions that you start with will basically lead you to the gas leaking out into the entire room. Okay, so it also becomes clear that it is exceedingly unlikely that the system will fluctuate back to the state where all the molecules were confined to half the room. Okay, because if you wait long enough, presumably, like you can imagine that the gas will, in its random motion, whatever initial condition you start with, it might end up in some corner. But that is unlikely because the number of particles is so high. So, it is that's a very unlikely configuration, precisely because there are way more states in which the gas the configuration of the gas corresponds to it being distributed everywhere in this room. So, and this is basically what we have explained. So this is an explanation in some sense of the second law and the arrow of time. But so this is sort of the conventional, this is how we typically understand arrow of time or the second law of thermodynamics. But this is not a complete explanation. And this comes back to what I said here, that there are two distinct aspects. Okay, we have explained that certain initial conditions are special. So those initial conditions are ones of low entropy. And if you start there, entropy will always increase. That's what we have shown. But we have not really given an explanation for why is it that we seem to find many initial conditions which have low entropy. So this is what is the real puzzle at some level of the arrow of time. Okay, so this is the second part of the question, or more correctly, I think it is the first part of the question that I asked there. Second part we have answered. The answer to the second part is basically that, some configurations, if you have low entropy, it is natural. There are various initial conditions with low entropy, and if you start there, it is overwhelmingly likely that you will increase in entropy or increase in the arrow of time. So that explains why when you start from a table with a glass of water and it falls, it will basically go into a configuration of higher disorder or higher entropy, and so you will find this.
Okay.
So
did we answer why that is in the sense why nature prefers maximal entropy? So we are just attributing the same question to different.
I think that we can explain because there are more microscopic configurations corresponding to those systems. That's essentially the definition of high entropy. High entropy basically means that there exists more configurations which look macroscopically similar. So it is there, I think at one level you could ask this question of the statement of what is the definition of a macro state, right? You could always ask that as that question. So why is it that we are some states are, so if you only had access to microscopic information of a state, there is no notion of entropy, right? So it is crucial for the definition of entropy that there is some macroscopic large scale world, and that could be a deep question. You know what I'm saying? There is a large scale we see some macroscopic we describe our nature essentially through macroscopic data, like the energy sliver in the microcanonical ensemble that you are asking, or some temperature in a canonical ensemble, or some other conserved charges, total conserved charges, etc., etc. So this is the kind of thing that like you can talk about all the things that we really talk about. They are all, roughly speaking, all the things that macroscopic things that we talk about, they are all basically things which we have access to as somehow classical large observers. Okay, so you could ask this question, why is it that this is necessary in the first place? And I don't think there is a fully satisfactory answer, but it might require basically more thought. And there is some effort in that direction in statistical mechanics and so on. People who work on statistical mechanics and non-equilibrium statistical mechanics, etc., people think about these things. But so my focus will be slightly different. What I will try to do is that, okay, let's assume that there are well-defined macroscopic descriptions of states, which is essentially like, like the room, at least it's a phenomenological fact that describing the temperature, energy, etc. of this room is a well-defined way of describing the gas of molecules in this room, or this, this gas of molecules in this room. But it is also true that there is a microscopic description of the state, which is about specifying all the velocities and all the positions of all the particles at some time. Okay, so if you give me the second description, it turns out that there are many of those second descriptions which correspond to essentially the same large scale description. And that's where, so in that sense, once you buy the fact that there is a macroscopic description, it is no longer a puzzle that there is, entropy increases in evolution. Because that it really is saying is that macroscopic states with more microscopic configurations are just more. So if you start with a random initial state, generically speaking, it is plausible that you will flow in that direction in evolution. So, but I guess the question that you could ask at a slightly deeper level is that what is the natural way to distinguish between macroscopic and microscopic descriptions of nature? And that I don't think has been sufficiently clarified. And I think it might be related to the origin of classical world in quantum mechanics. So these are, fundamental questions. There might be something there, but that's not the direction that I will be talking about. I'm going to take a slightly more conservative point of view, which is that let's, assume that macroscopic configurations exist as statistical mechanics seems to see. And then, you have this notion of entropy increase due to time evolution. But then you have to ask the question, why is it that certain initial conditions with small entropies are preferred in nature? So that is the question that, so we want to ask questions so that at least we can get towards a sharp contradiction or a sharp puzzle. So that's the direction that I'm going. Do I answer your question at least partially?
Yeah, my question was why nature prefers more disordered state in the sense as a finite state.
Right. I mean, I'm saying that once you define a macroscopic state, that's a tautology. I'm saying that once you define the notion of a macroscopic state, and when there is this notion of microscopic description as well, then it is a tautological fact that evolutions will typically drive you towards that, right? So the question is, what you're asking, I'm saying, is basically the question of why does there exist this macroscopic description? If your only description was the microscopic description, why is it that we seem to be able to describe large-scale behavior of nature in terms of some other quantities like energies and charges and temperatures and so on and so forth? So that is not so completely, I would say it's not a fully resolved issue. So, but once you buy the fact that there is a macroscopic description, I think it is a tautological fact that small, the states with small entropies will automatically evolve. States there are some macroscopic states which are represented by smaller number of microscopic states. So if you start from there, so then basically you will go somewhere else. So that is, I find that, I don't see there is I find it to be tautological. It's essentially the buying is basically happening in describing the state, the state in terms of a macroscopic description as opposed to a microscopic description. So if you only have microscopic description, we have no access to that. But somehow we are making the claim that there exists a macroscopic description. Then there is a question of how many microscopic descriptions can realize it, and the state where more microscopic descriptions, realize the macroscopic state is where dynamics will typically drive it. So that's a statistical statement, and that's that is, I think there is no puzzle there. The question is why are we choosing these macroscopic states, and that I think is a more conceptual question. Okay, so okay, I think I have explained it to the ground. So
sir,
yeah, sorry.
Sir, I have a doubt. So you told we have some we don't know why there are some low entropy initial conditions. But if they are there, then doesn't that mean there are even lesser entropy initial conditions which lead to the lesser entropy initial conditions? So doesn't that mean it has to start somewhere, right?
That's an excellent question. We'll come to that. That's an excellent question. So so yeah, so let me I will get to that, but probably not answer it sufficiently. But so yeah, that's a great question. So what we have failed to explain is why is it that we seem to run into such unlikely initial conditions in the universe around us? Okay, so this is, I'm not immediately answering your question, but I'll get to it in a few slides. So we do not have an answer to this question. Okay, why is it that unlikely initial conditions exist in this in our universe? It just seems to be an accidental fact. So because if you just assume that, oh, okay, our universe was made of the most probable initial state at the moment, then we will just see global thermodynamic equilibrium. All the gas will be just like the universe will be essentially be empty. Okay, so so there will be no galaxies, there's no nothing. So it just seems to be an accidental fact of nature that we seem to be living in a universe whose entropy seems very, very far from a configuration of maximal entropy. Okay, maximal entropy means global thermodynamic equilibrium in some sense. Okay, it can even be an empty universe where all the radiation has escaped and all the stuff has escaped, all the black holes have evaporated and so on. But our universe seems to be a system that is far from equilibrium. That's an observational fact. Okay, the reason why anything at all happens in our universe, the formation of stars, galaxies, life, intelligent life, etc., is a result of the fact that our universe is far from equilibrium. So what we know about entropy and the second law also means one more thing. The entropy of the universe was lower yesterday than it is now. This is kind of related to the question that was just asked. So extrapolating this backward, we come to the seemingly inevitable conclusion. At the beginning of the universe, the Big Bang was an exquisitely low entropy state. This might be a little surprising because you might think that many people think that the Big Bang, because it's an explosion, it is entropy is somehow high, right? It's a very hot, dense gas, basically. But as you will see, it is not. It is actually an extremely low entropy state. And that is necessary, first of all, to explain why our universe is out of equilibrium. Okay, our universe apparently is an exceedingly improbable one. The Big Bang that we started with is a very, very, very low entropy state. So again, I want to emphasize that there is no contradiction here. This is not a violation of the laws of nature as we know it. It is just that our initial conditions seem exquisitely fine-tuned. So if you want to believe in God, this is a good reason. Or if you want to understand it, then you can understand that. You can try to understand that. Generally speaking, I think the history of science has always been trying to eliminate God from places where it inhabited. And I think this is one of those places. So we simply are not satisfied with the answer we have found because we would like to know why the universe started there. Okay, so you could just leave it as an explanation, without explaining, because there is no contradiction there. I really want to emphasize that, which is that if you had a very fine-tuned initial condition at the beginning of the universe, we would actually see the arrow of time as it exists. Okay, so but that is not a satisfying answer. We simply are not satisfied with the answer we have found because we would like to know why the universe started there. A situation where we have no sharp contradiction, but we get the nagging sense that the nature is not quite, it's not quite, it's not a satisfactory answer. That is sometimes called a fine-tuning problem. And this is an example of a fine-tuning problem. Why is it that the Big Bang seems extremely fine-tuned? The idea that the universe started out in a very low entropy initial state is sometimes called the past hypothesis. Okay. So, and in some sense, I also want, people often talk about fine-tuning in the Higgs, particle physicists talk about fine-tuning in the Higgs, and cosmologists talk about fine-tuning in the cosmological constant, et cetera, et cetera. So one of them, the Higgs fine-tuning, if suitably defined, it's 1 in 10 to the 17, and the cosmological constant, again, suitably defined. Some people will quote it as 10 to the 120, but I think it's better to quote it this way, I think. So, I mean, depends on how you think about it. But yeah, so, there are a few different ways of thinking of the fine-tuning problem, but whatever it is, they're huge. Okay. So, but the fine-tuning involved at the beginning of the universe, at the Big Bang, is something that is, if you want to explain the times arrow that we see in our universe, then that fine-tuning, if our conventional physics is to be believed, and I think it might not be believable, is some ridiculously large number, and it requires various approximations, assumptions, etc. So this is not really taken to be, it should not be taken at the same level of precision as the 10 to the 30 and the 10 to the 17 that I wrote here for Higgs mass and the cosmological constant. So this is like a ridiculous number, and it involves various crude assumptions, etc. But the only thing to take away from it is that it is a vastly huge number, bigger than pretty much any other number that we have in physics. Okay, it is much bigger than, for instance, the cosmological constant problem, which is often presented as one of the biggest fine-tuning problems in nature. So, so that's what that is. So, so this sort of answers the last question that was asked, which is that, or does it? It doesn't answer, but it addresses. So the question was, why is it that, if our initial conditions are fine-tuned now, they better be even more fine-tuned a couple of days ago, right? I mean, and that is true. And if you trace it all the way back, the original starting point of that is the Big Bang. And we believe that there was, at least if our standard physics picture of the standard cosmology is true, we have a burden of explaining, if we choose to view this as a problem, of how much fine-tuned the initial conditions of the universe was. And I think there is a real opportunity for doing science there, I think. Yeah. So, yeah, please.
So it's also, maybe it's not a doubt, it's maybe a comment. It's also a problem of observation, right? If we are not in the first place to observe it, there is no fine tuning, right? Also, we don't know this is the actual fine tuning or there is exists some other fine tuning, right?
What do you mean? I mean, so this number that I quoted is kind of like a very crude estimate. But there is it's like there are various things we don't understand in detail about the universe, especially the earlier parts and so on. But the number is humongous is the only point. So it is basically the only point here is that the number, the fine tuning involved in in the initial conditions of the universe, if we want to explain the arrow of time that we see in nature, is very, very large, is the point. So so that's the second part of the question. I think so. I don't think the question is not so much whether we know all the details in order to compute it precisely, but the details we know are sufficient to put essentially like some lower bound on how fine-tuned it should be. That's how you should, roughly speaking, think about this number. It's huge. That's the only message. But the first question you asked, I forgot what was the first question. Can you repeat that?
No, I was asking like that. So the choice, like, so we are, if we say there exists some, there can be exist some other more fine-tuned initial state, or it's just a matter of observing, right? If we are not observing,
there is one could argue. See, the universe will be very different if it started in a slightly different way. So, like, yeah. So, I mean, I'm not quite understanding your question. So, the point: are you trying to say that, like, how the initial, if we knew more, somehow the initial condition, the fine tuning would be different? That is true. But the only point we are making is that there is a fine tuning which is humongous. We are not trying to be very precise about what exactly or how much exactly the fine tuning is, because that requires very detailed knowledge of various things. But that's the point, right? Yeah. The point here is basically that, like, just from the existence of the arrow of time, we can argue that the Big Bang is an exceptionally fine-tuned quantity. And I don't think you should take this number very seriously, because I mean, Penrose put in various crude assumptions, this, that, whatever, and some of those might even be wrong, and yeah, so it depends on the specific models that we assume for the universe, etc., etc. So, but the point is that at least prima facie there is a problem, which is the problem, or at least I again want to say that I keep saying problem, but what I mean is that there is something it would be nice to understand it. It's not a contradiction. So the number, don't worry about the number too much. It's the point is only that there should be some fine tuning in the early parts of the universe so that now we see an arrow of time. That's essentially the message. Okay.
Thank you.
Yeah. So yeah. So the reason why I wanted to emphasize that, because even practicing physicists, I have had this experience, which is that they often carry the impression that Big Bang was a situation close to global thermal equilibrium, which it is not at all. Okay. So this is it's very easy to think that, because Big Bang is generally like, you think of it as a hot, dense gas, or, like some essentially extremely hot radiation at least in some parts of some phases of some eras of the Big Bang. It's a very hot, dense, gas. So you might be, and in fact, you often make assumptions of thermal equilibrium in order to make calculations. But I will tell you what that is. It's not quite that those calculations are correct, but there is one fundamental aspect which they don't need to take care of in those calculations, is the reason why this entropy is actually low. Okay. So the point is that, like, just because things are, dense, and they are basically thermal equilibrium, gas and thermal equilibrium, it is tempting to believe that the universe was kind of in thermal equilibrium in a global sense at the early part of the universe. This is kind of related to the fact that Big Bang in our mind kind of conjures up visions of a messy explosion with a lot of high temperature stuff, and high temperature you kind of psychologically we associate it to high entropy state. So yeah, so it is also because, yeah, this is what I was just saying, which is that we also treat the matter present in the early universe as being in local thermal equilibrium. This is indeed reasonable, because that's how we talk about how various species decouple, come out of equilibrium and so on and so forth, and all of that is reasonable, because the expansion rate of the early universe was small compared to the temperature of the time. So matter had time to come to equilibrium with itself at that time. Okay. So, but the key point is that if you assume, because of these reasons, that the very early universe was in a high entropy state, then you're wrong, because that's in direct contradiction, first of all, because it is direct contradiction with the existence of the arrow of time in our universe, one. And secondly, and this is the fundamental dynamical reason why this is not the case, is because people make this mistake because they forget the very key player in the early universe, and that is gravity. Okay. So if you just had a gas in a room and there was no gravity and you heated it up, the system will be in some, the gas being in equilibrium, distributed uniformly everywhere, is actually the equilibrium configuration. But when gravity is present, this is far from equilibrium. For systems with gravity, a roughly uniformly distributed gas of matter is not the highest entropy state. And this fact is sometimes called Jeans instability, because the gas is an instability towards gravitational collapse. Okay. So the highest entropy state of a gravitating gas is when the gas has collapsed to form a large black hole. So that's the configuration that is maximally entropic when there is gravity is present as well as matter. So we are not talking about just the equilibrium associated with the matter. We are also talking about the gravitational dynamics of the full system. And in such a configuration, Big Bang is a very, very low entropy state because it corresponds to a gravitating configuration where the gas is uniformly distributed, which is very, very far from equilibrium. Okay. So the puzzling thing about the early universe is that despite the fact the most entropically favored state for the matter in the early universe was a collapsed black hole, we find instead that the matter was extremely uniformly distributed at the Big Bang. Again, this is not quite a contradiction, because even in gravitational systems, you can choose initial conditions which are fine-tuned. So it's just shockingly improbable. Okay. So this is so one thing I think that if you want to take away from this lecture, which I think it's like I've often found that people don't seem to fully appreciate this fact. Penrose emphasizes it, but the thing that I think is that somehow the initial condition of the universe, people often think of it as global equilibrium. It is not global equilibrium because there is gravity. So because when gravity is there, the fact that the Big Bang happened is a fine-tuned phenomenon. Okay, so if you have any questions, you can ask me. I mean, I think I'm doing okay as far as time. Another 5 minutes, I'll be done. So in fact, the cosmic microwave background, which you can think of as the afterglow of the Big Bang, which is something that this WMAP and Planck and all those satellites have measured. So let me not make comments about these satellites. These measurements show that indeed the early universe is extremely homogeneous and isotropic. So even though there was gravity, okay? So is there a theory or a paradigm or an idea that one can use to understand why the entropy of the early universe was so small? As far as I know, there is not, okay? So the initial theory of initial conditions is something that we don't really know much about. We don't have any theories of initial conditions. What we have is we have theories for dynamics or equations of motion, and then we specify initial data or boundary data as an external input. Okay. So I think that we don't have good theories for it. And this is one of the places where it seems like it is necessary that we try to understand the status of initial conditions as well, and not just the theories themselves. Okay. Yeah. So, I mean, let me make, there is a comment about inflation here, but let me not dwell on it. Yeah. So sorry.
I have a doubt about.
Sure. Go ahead.
Yes, sir. Is entropy one of the reasons why ancient supermassive black holes were not being explained? Cannot be explained.
See, supermassive black holes are still tiny compared to the entire universe, right? Supermassive black holes, even within the galaxy, supermassive black holes are very, very small fraction of their mass. I mean, I'm not an expert on this, but I'm this particular statement I'm fairly confident about. So supermassive black holes are still, it's a very tiny fraction of the total mass energy of the universe. So in that sense, they are still not enough to explain this entropy question, because all of these things are, the universe is a humongous place. So even though there are many black holes and even supermassive black holes, they are really like, almost nothing compared to the total amount of energy and entropy in the universe. So in that sense, supermassive black holes are more like a footnote to this discussion than the whole thing. So what I'm talking about is the full entropy of the universe now, for instance, as opposed to what it was at the beginning of the universe. Again, I mean, this number is, like I really should emphasize that this number is, can you see my cursor?
Yes, sir. Yes.
Yeah. So this number is nowhere near on as strong a foundation as these two numbers. These two numbers are perfectly well-defined numbers. We know this because the mass of the Higgs is 125. So GV. So because of which we can fix this number precisely if you like. If you know, precise number doesn't mean much there, but we can do that. So here also the cosmological constant, also you can actually fairly easily make fairly robust estimates. And if you do it in certain ways, you will find that it is 10 to the 120 in some units. Okay. And this, I have written it in some square, the fourth root of that is what I have written basically as 10 to the 30 here. So, but this number on the other hand, it comes with various ambiguities and assumptions and this thing and so on. So it's not on the same strong footing as this. The only reason I put it there is that at least there exists an estimate by somebody, Penrose in this case, which is that the fine tuning at the early universe was very large. So, and that's a plausible statement because as we know that the arrow of time requires an explanation. Okay. So that's the only thing I was saying there. So, so I don't know whether I answered your question. Yeah.
Sir, it was you explained it nicely.
Okay, thanks. So, was there any other question?
I have a confusion.
Yeah.
Actually, as I understand, you are talking about thermodynamic entropy, right? So when we go back in time and we speak about the early universe, then do we need to incorporate this entanglement entropy? Because
entanglement entropy, it depends on which state you're computing it in. So entanglement entropy is, from this point of view, it is, it's mostly about splitting the system into two, multiple pieces, and then talking about some particular, like if you have a Hilbert space, you can split it in various ways. Here I'm talking about something more like, it is basically, as you were saying, it is basically thermodynamic entropy. The statement, there is no sharp statement of the kind that we have for second law of thermodynamics. There are analogs actually, like I'm being slightly vague here, but it is nothing as powerful as the second law of thermodynamics for entanglement entropy. So nothing as universal and so cleanly stated. So the puzzle is in the language of thermodynamic entropy, which is why we need to focus on an explanation in that language. So you can ask questions about entanglement entropy in the early universe, and people do. But the problem is that as long as you don't connect it to thermodynamic entropy and have a statement about the increasing entropy as time evolves, increasing thermodynamic entropy with time evolves, and the second law of thermodynamics and the arrow of time, it is not clear how exactly entanglement entropy is going to help us. Entanglement entropy is a perfectly well-defined quantity. You can, in principle, compute it. There are questions about how entanglement entropy can be defined when there is dynamical gravity, etc., when general relativity is also there or quantum gravity is there and so on. So those questions are not so well defined. It's not, people don't understand how to do them. But I'm saying that, like, even at a more basic level, because the puzzle is the contradiction that we have is in terms of thermodynamic entropy. So somehow we have to find a resolution for that. Even if, at intermediate stages, we talk about, entanglement entropy or von Neumann entropy and whatever. So that we can talk about, but the resolution ultimately has to come from here. So, which is why I'm formulating all of these questions in the language of thermodynamic entropy. Does that answer your question?
I'm confused about, I'm confused about whether can we talk about the thermodynamical system even before this radiation dominated epoch, right? When we talk about the starting of the universe.
Yeah. So I think that is a good question. And I think it is related to your previous question, which is that how does one associate macroscopic quantities, right? So the question is, what exactly does a macroscopic state refer to? And we generally have intuition for that question in limits where gravity is very weak. Okay. So the question is, like, again, the question of, if you do not have a notion of macroscopic state, you cannot define a coarse-grained thermodynamic like entropy. So and this is where the necessity of understanding what a macroscopic state actually means in the setting of gravity, for instance, comes up. So, and that I don't think we have a very good answer. So it's all of these questions are related, but at the same time, your question is basically, I would say, the same question that I think you asked earlier, which is that why is it that so which is again a question about the existence of the macroscopic state. Why is it that nature prefers, you asked it as a question of why is it that nature prefers higher entropy configuration? That is basically the statement of asking, there exists some preferred class of macroscopic states which we think are what we see around us, and why is it that once you believe that, microscopic evolution will drive you towards that. There is no puzzle, but the puzzle has sort of been shifted to the question of what constitutes a macroscopic state. And that's really the puzzle, even in the context of this early universe situations where there is dynamical gravity, which is a very exotic situation for us, where, you know, compared to what we have around this room or something, where generally we can just assume that the limit where the gravity is very weak, and this is basically just a standard, macroscopic states or macroscopic states which correspond to what we are familiar from, let's say, field theory or something. Okay, field theory or particle physics or kinetic theory and so on, where we have this idea that, specifying temperature, energy, etc. are sufficient to describe the macroscopic state. But the question is, once you have dynamical gravity also, it is less clear what the right thing to do is. So, I mean, entanglement entropy exists, but I'm saying that, unless you make a precise statement about how it connects with the thermodynamic entropy of the macroscopic state, it's not, I'm sure that it is relevant, but how to connect with it is the question. Fine.
Okay, thank you. Yeah.
So in the next slides, I'll just make a brief speculation and I'll conclude there. I'll leave you with that might be relevant for understanding the entropy in question. And this is sort of like, it's not super original or anything. It has been around in maybe some version or the other, but I think that I'll phrase it as a very stark statement. And so the good thing about stark statement that they could be wrong. So by proving that something is wrong, one can basically make progress. Okay, so one of the reasons why I kind of had, I thought it should be made sharper at the time. I got distracted by other things. So that's one of the reasons why I thought I'll talk about it. So other people who have had similar ideas are, Banks and Fischler, and Samir Mathur at Ohio has had some ideas like this. Naoki Sasakura, I think I made this slide some time ago. I don't remember his papers now, but I'm sure he also had some similar statements. So this is, let me just state what the key observation is. The key observation is that uniformly distributed gas is in fact the highest entropy state in a world without gravity. Okay, so that's the reason why early cosmology and various species decoupling, etc., the calculations that cosmologists like Jishnu, for instance, do, they are perfectly valid because we are assuming that the matter is coming out of equilibrium. Various pieces of matter are coming out of equilibrium as the expansion rate of the universe decreases with time. So indeed, this is the reason I emphasized that point earlier. So if there was no gravity, it is immediately clear that the initial conditions of the universe are precisely the most natural, unfine-tuned, high entropy ones. Okay, so this is something that we know because the universe matter was essentially in thermal equilibrium. So this raises the possibility that perhaps the Big Bang should be viewed as a switching on of gravity. Okay, so this is where the speculation sort of comes in. And we don't have any particularly nice way of implementing this. I really want to say that. So we don't fully understand how to do that, but I'm just suggesting that, and not just me, other people have also said this before, which is that, is there a way in which it seems kind of plausible, but it's not clear how to make it a precise question. So once gravity is turned on, now the system of gas, which was in a high entropy state, ceases to be a high entropy state, and instead it becomes an extremely fine-tuned state. Okay. This is because now for the gravitating gas, the highest entropy state is a gas of black holes, or a gas of black holes, or even a big giant single black hole. That's the highest entropy state. In fact, this statement is wrong. It's not necessarily the highest, it's not a gas of black holes. It's the big giant black hole which has gobbled up everything. That's what the highest entropy state is. Okay, so the Big Bang was so is there a way to make it precise? So I will just leave you with that question. I'm not claiming that I have a very sharp answer or even that this question is necessarily in the right direction. But it seems almost tantalizing that, the initial state of the universe, the matter part is sort of completely in equilibrium, but the moment you turn on gravity, things turn to complete chaos. Complete chaos, or the universe is very fine-tuned. So, okay, so this is my last real slide. So the take-home message, the fundamental laws of nature are time reversal invariant, but the world around has an asymmetry between the future and past. So this is something that you all know. And just these two simple facts lead us to a pretty remarkable statement about the early universe, that the universe started out at a very, very special state. Okay, if we assume that the conventional explanation for the second law of thermodynamics in terms of microstates and macrostates is still valid. So that's, I think Ratul's question was kind of on that. So, and there are certain loopholes there, but if you are staying conservative and if you believe that the microstates and macrostates, the understanding that the tension between them is what is responsible for the arrow of time, then we are inevitably led to this question of why is it that the universe started out at a very special state? And while this is not a contradiction with anything we know, it is something that would be nice to understand. Okay, so that's a fine-tuning problem. So so it seems plausible to me that there is something deep that we are missing, and maybe we can understand something more by looking at it. Okay, so that's where I'll leave you. Thank you very much for your time.
Thank you, sir.
Yeah.
Okay. Thank you very much, Chethan, for the nice talk and clarifying doubts. So, is there any more questions from audience side?
Yeah, I have one question. Recently I came across, I just started it, but recently I came across something called rigged Hilbert space and
What is it?
gamma vectors.
Came across something called rigged Hilbert space.
Yeah, rigged Hilbert space and gamma vectors. And
I know nothing about them. I was in when I was in Austin, when I was doing my PhD. I think David Bohm was a big proponent of rigged Hilbert space. So, but I have to say that I never really paid much attention to it. You'll have to explain to me what rigged Hilbert space is.
I'm also just started it, but so what I read on those documents that said, quantum mechanics essentially is this time invariant. So for that, like you can take Schrodinger equation forward and backward without any problem.
Yeah.
But
Yeah.
once you have such decaying state, for example, decaying of muon or something like that, it is not. You cannot use linear quantum mechanics or Hilbert space or Schrodinger equation to solve.
I mean, I think, yeah, so that, I think I remember now why I was not really a fan of this rigged Hilbert space. Okay, so I think the point, see, somehow like that statement, basically like decaying states, you know, the question is how did you form the decaying states, right? In quantum field theory, we have like, you know, ways of understanding particle decays. So the question is, so when people say that there is no way of understanding decaying states, they want to think of those initial states as not part of the final scattering states. That's what the real sort of the puzzle, or, you know, so I mean, I don't know whether that is such a, you know, conceptual issue in the sense that, you know, somehow we have to form decaying configurations as well. We form them routinely, right? So like it is not that we cannot assemble, let's say, some heavy particle or a heavy nucleus or something which doesn't decay, because we know what the ingredients are, and they do form, for instance, in the core of stars, or in various, you know, there are, even in experiments we can form them. So it is not true that if you want to view a decaying state as only existing in the past but not in the future, then there is a, you know, tension. But I think that it's like it's kind of an example of a, you know, situation where we are you know, this is an explicit breaking of time invariance, and I'm not sure that we are ready for that yet. It is, you know, maybe it is a prejudice, but I don't find it compelling.
Yeah,
so
that's what I want to ask, because I find that like I want to ask about the applicability of that theory.
Yeah, but so I don't really know too much, but I'm saying that the premise never attracted me much. That's what I would say.
Okay, so I recently some paper came out, and basically what they do, they have some nonlinear material and they shine laser. At some point, the laser will break and form shock waves, and they explain the shock wave using these gamma vectors, in terms of gamma vectors, not in terms of Schrodinger equation. So it's recently started to get
the point
attention.
is that in standard quantum mechanics also you would be able to explain that, right? It's not like some phenomenon which only can be explained with this. They can explain it, but they can explain it also in standard quantum mechanics. The standard quantum mechanics has way more evidence than any particular thing of this kind, right? So I mean, see, the point is, as I said, you know, like if you I think the challenge always is to make progress while being as conservative as possible. It is yeah, I don't know. I mean, I you know, I think, yeah, I mean, I haven't really no comments to make about that. So my feeling or my prejudice, may call it prejudice, you know, like these are biases that one has to make while going about these things. So I don't find that to be sufficiently compelling that to, you know, quantum mechanics is one of the most well-tested theories. So it is not so easy to kind of come up with some modification which quantum mechanics cannot explain. All the mesoscopic physics that, you know, quantum mechanics can perfectly explain. So it is just that you maybe have another model which also explains it, but then the burden is on you to come up with a model of, for instance, a standard model, which is a fully quantum mechanical theory. So, and there we have explanations for decaying particles, and not perfectly in some cases, but it is like we have at least a philosophy of how these things work. Okay, so you know, it's hard to predict where our gaps in knowledge necessarily are, but I'm just saying that I don't feel like that's where it is. So that's what I would say. Yeah.
Okay. Thanks.
Arun, can you please introduce yourself? Where are you from and what are you doing, etc.?
Me?
Are you talking? Sorry.
I mean,
Sorry?
Arun, you're Arun, right?
Yeah.
Can you please introduce yourself? We would like to know what are you doing, etc.
Okay. Yeah, my name is Arun, and currently I am doing research in University of Twente, Netherlands.
University of where? Sorry.
Twente.
Where?
Twente, Netherlands. Twente.
Yeah.
Yeah. So I'm working on quantum security and QKDs.
Yeah.
So on.
Yeah, I should just add that, you know, my knowledge of these things is that you're asking questions about things which I don't know anything about. So I think that, you know, like I'm trying to always interpret or look at things from a sort of a particle physics kind of perspective. So, which is why, I mean, I think that, you know, so like, I find it very hard to kind of think that mesoscopic physics would affect fundamental physics. So it might be a prejudice. So, I mean, you know, like my ignorance should not, you know, stop you from forming your own opinions in this kind of thing. So I just wanted to say, I really don't know anything about it. So your question was kind of from something that I know nothing about, so I don't really have much to say. That's more.
I also just started to look in terms of this time reversal and also.
Sorry?
I just started to look in towards this time arrow of time thing. So I'm also not very well knowledgeable.
Yeah. So yeah, arrow of time is I mean, there is actually a book by Dieter Zeh, which is quite philosophic and so on. So it's a difficult book to read because it's too wordy, but it's a book which has some discussions on this kind of thing. But I'm kind of interested in very pragmatic things in the sense of like, you know, like can we construct explicitly a model which explains this arrow of time in a simple way or something like that? So yeah.
Okay. So maybe we can have one or two questions.
Yeah.
Is there any question?
Yeah. Thanks.
Okay, I don't see anyone asking any questions.
Hi, Chethan. Thanks for the wonderful talk. And I just want to ask,
Krishnan, right?
I just want to, So I just want to understand what you were trying to say. So especially the fine tuning problem or the low entropic initial state puzzle, is it only associated with the early universe, or early universe scenario is just one toy model you can come up, or
no?
So these kind of fine tuning is inevitable in any gravitational system.
So it is fine tuning as long as there is a Big Bang, and also like, I mean, there is essentially only, see, the precise number of the fine tuning, forget about it. I mean, it's just, I think, you know, something Penrose cooked up. But the point is that the initial, you know, so our universe clearly has an arrow of time, and we know that the entropy yesterday was higher than the entropy today. So, or at least it seems like that. You know what I'm saying? So again, questions are always a little bit. These questions are always a bit confusing when there is gravity. So you could ask this question of what is the global entropy of the entire universe? We don't have a very well-defined way of saying anything about that. So, but I'm saying, you know, like if you naively extrapolate what we see around us about the fact that, you know, if you look at the past, it looks like entropy is decreasing. And then you trace it back all the way back to the Big Bang, then it must necessarily be the case that entropy is decreasing. So if you just believe in the second law of thermodynamics, right?
Okay.
And there exists some thermodynamic entropy, then it is an inevitable fact that at the more into the past that we go, the entropy must be low. So that's maybe the point in some sense.
So maybe my question is like, is it an empirical fact or the property which we are yet to understand about our universe, or can we come up?
It is not quite an empirical fact in the sense that, you know, do we have a way of measuring entropy at the early universe? We don't necessarily have that. I mean, there is various approximations, assumptions, etc., that people make, and that is kind of how Penrose makes that calculation. But I'm saying that it is an overwhelmingly reasonable guess, right? In the sense that, like, if you take it to be if you take our universe to be increasing in entropy as time goes by, Which is something that we genuinely believe based on all the. So in fact, I mean, you know, second law of thermodynamics is something that people believe even more strongly than people believe quantum mechanics. Second law of thermodynamics, nobody knows any counterexamples, right? So, because of it, you know, if we don't buy that, then the burden again shifts to like, why don't we believe that, right? So my strategy or kind of philosophy into this kind of thing is always to apply these ideas to take them completely seriously until they finally explode in your face. So you should not give up on them until they actually blow up in your face. And what is interesting is that even if you push it back all the way to the Big Bang, the second law of thermodynamics doesn't quite seem to break. What it really is giving you is that there is a fine-tuning problem, which is not quite a contradiction, but something that sort of begs for an explanation. Why is it that there is a fine-tuning, right? So
So the question was really, are we actually pushing towards the direction of some properties of universe which we are yet to understand? Or I think my question was, can we come up with a toy system where whatever you have been discussing so far can be fully understood or developed?
That is, you know, so I think such models might exist, but it is always tied with the fact that it is very difficult to come up with toy models for gravity. So, you know, like the problem is usually always related to the fact that whenever there is gravity involved, we don't have good toy models. Because, I mean, you know, like for instance, people talk about various models, and that's one of the things that people do, for instance, in string theory and so on, to come up with models like SOK model or, you know, the three-dimensional gravity or various toy models, which actually capture some aspects of it, you know? So the question of gravity is that the moment you make it a toy model, it is, you often want it to be in a fully quantum mechanical setting. Classically, general relativity is a perfectly fine theory, but then you run into this kind of contradictions. Contradictions are at least puzzles. So then the problem is you want to, let's say you want a fully quantum mechanical system where gravity emerges in some way, and then you want to also do something with it, okay? But then the question is, if you want to make a toy model out of it, oftentimes what happens is that you end up throwing out some piece of the puzzle which may be fundamental. And that's, for instance, the reason why I've seen, like, I mean, you know, some people, I'm sure you've heard of it, like the things like ADS-CFT correspondence that we work on. The good thing about it is that it is basically a model which retains all the properties of gravity, but maybe in a universe with a negative cosmological constant and things like that. So which we've seen as lesser sacrifices than just trying to build a toy model for gravity where you maybe lose, you know, something like, you know, some fundamental property like entropy. Black holes don't exist. So there exist many toy models of gravity where there are no black holes. Then I think it is not very interesting. You know, for instance, you know, there are low-dimensional simple models in string theory where you have, you know, where you do have good quantum mechanical models of gravity which are quite under control, but they are somehow too trivial in the sense that they don't contain black holes. We want a system where there is gravity in some sense, but we also need black holes, because black holes, we believe, are so fundamentally an important part of the puzzles associated with gravity that if you don't have, if you have idealized your gravity so much that your black holes are thrown out, then I think there you will learn something, but may not be the most fundamental thing. So that's
and these kind of questions cannot be asked in such toy models. That's what you're thinking. Like the fine-tuning.
It may be possible. I think that building good toy models for gravity, I think it is a very interesting question. So, and I think people do, you know, but how do you make the, for instance, one of the ways in which you make a toy model is by reducing dimension. For instance, three-dimensional gravity is a good toy model for various things. Okay. So three-dimensional gravity may be a good setting, I think, in order to answer this, because three-dimensional gravity has one good property, which is that it doesn't have propagating gravitational waves, which makes something simpler. And my suspicion is that it doesn't make the fundamental problems go away. So the problems are still there. We are just getting rid of some technical problems. Like gravitational waves essentially means that there are some nonlinearities or some perturbative aspects we are ignoring. But I think main problem, because in in 2+1 dimensional gravity, there actually exists you know, universes which are kind of like cosmologies. They're doing it. It might be worth studying.
I see. Okay, thanks.
Yeah. Thanks.
Okay. Thank you very much, Chethan, and all of the participants. We had very good discussion today.
Yeah.
So we
thanks
hope
for
to
all the questions.
collaborate.
Without the questions, I think it wouldn't have been fun for me.
Yeah, it was very interactive.
In that
Is there
case,
any
I
other
also have one question. Can I ask?
Yeah, fine.
I think there is
Yeah,
one.
but
Please ask.
I
Yeah.
think it's not related to the talk, but there is something that often confuses me, because when I go for a lot of these kinds of cosmological and astrophysical talk, people often say the total energy of the universe is zero. Can you just
Yeah, I
explain?
mean, I don't know whether that is, it's not so easy to define the total energy of the universe. So what people roughly speaking mean is that, like, what they really mean by that statement is that the Einstein equation holds. That's what really it means. Like, so the global energy of the universe is a difficult thing to define. So part of the reason is that, so for instance, if you have a universe which is like, asymptotically flat, that's a technical word, which means that if you're, far away from all matter, the universe was just like Minkowski space. Like Minkowski space means, the space-time of special relativity. So if, like if it was asymptotically flat, then we know how to define total energy, etc. for the universe. But on the other hand, when you have people try, but I don't know whether there is a compelling definition or a completely, a definition of energy in expanding our cosmological universes, which is like as well defined as it is in, let's say, this asymptotically flat or asymptotically ADS universes. So those kinds of, there are some classes of universes where we know how to define total energy very well. But I don't know whether it is, it's completely settled. The question of maybe Jishnu or somebody will know. So that there is whether the question of defining total energy in, Robertson Walker, which is our kind of expanding universe, where that kind of universes, I don't think there is a well-defined global notion of energy. But what often people mean by the statement that the energy of the universe is zero is, in some sense, you could say that, you could think of Einstein tensor, the r mu nu minus half g mu nu r, as the stress tensor corresponding to the Einstein-Hilbert piece in the action, right? So if you have a Lagrangian, if you're not familiar with this, this Lagrangian formulation of general relativity, don't forget about what I'm saying. But in case there is some of you who are familiar with this, what is basically the case is that if you have an Einstein-Hilbert Lagrangian with some matter part, you vary that action with respect to the metric. The matter parts variation is what is called the stress tensor, or which, roughly speaking, the energy. So the Einstein part will give you what is called the Einstein tensor, which is r mu nu minus half g mu nu r. Okay. So what oftentimes people very crudely mean by the statement that the total energy of the universe is zero is just the statement that Einstein equation holds. Okay. So g mu nu plus t mu nu or whatever, g mu nu is Einstein tensor plus t mu nu, which is basically the stress tensor of matter. So those two things adds up to zero, because you are kind of thinking of the metric contribution, the variation of the metric, the Einstein-Hilbert parts variation also as a sort of a stress tensor type contribution. If you do that, yeah, then it is true. It is tautologically true that the total energy of the universe is zero. But I think in order to properly define a total genuine energy, which is measurable in some way, that you can associate to the expanding universe that we live in, I think it is somewhat harder, I think. So that I'm not super sure whether people have managed to do a clean definition of that. So, but in some cases you can, and there it is, in many cases, it is not true that the total energy of the universe is zero. For instance, if you take Schwarzschild space-time, right? Schwarzschild is the most basic black hole in general relativity. So if you compute its total energy, it's not zero. It is some finite value, and it's the solution of Einstein's equations.
Okay. Thank you.
Yeah. I don't. Were you part of art program? Is that the same? I don't know.
Yeah.
Hello.
Hello.
Were you part of active research training program of KTPI? Is that the same? I don't know.
Yes, I was
I didn't
part of
recognize
KTPI.
you. Sorry.
Okay, it's okay.
Yeah. I didn't recognize.
No.
Yeah, Chethan actually he did project with us. As a part of active research training program of KTPI. Now he is doing PhD in
IISc.
other science.
Oh, I see.
No. I mean, part of active. There is an active research training program for MSc students. Basically, we offer MSc projects and give training them. So he was one of the participants. Yeah. So now he is doing PhD in Netherlands.
Oh, I see. Okay.
Yeah. Thank you, Arun.
So
yeah,
the
maybe we
general,
can wind
the
up
story.
now.
Yeah.
Sorry.
Sir,
No, I was just asking that most of the students who are present are basically PhD students or senior MSc students and so on.
That I am not sure. Mostly BSc, MSc students, I think.
Yeah. So I mean, I just wanted to, after giving the talk, I was wondering whether it was such a too low level or too, something like that. It is, yeah. Okay. But I guess there are questions. So I think
is the change in action from past to future in the expansion of universe is the same if reversed?
Can you repeat the question? Sorry, I didn't quite catch. I didn't understand what was the question.
The change in action in the expansion of universe from the past to future is same if in reverse.
Change in action. So in order to compute the action, I think you'll have to, basically integrate it across some spatial slice, right? So that may be a good question. I don't know actually. So because I think you can probably compute it, but the only thing is that in Robertson-Walker, it will be a divergent quantity. So you'll have to somehow regulate it because Robertson-Walker is spatially, if it is spatially flat Robertson-Walker, it's basically going to be a divergent quantity. So maybe there is a good way to define it. Like it will be in both, whatever time slice you compute it, the action will actually diverge because of the volume of spatial slice. But maybe there is a good way to regulate it, and maybe there is some interesting thing one can say. That might be possible. Yeah, that I don't know the answer, but it may have some interesting things to say there. Yeah.
Okay. If there are no more questions, we can wind up the session. Thank you, Chethan, for the talk.
Yeah, thanks for the invitation.
Okay, thank you.
Jishnu and
maybe we can.
Okay.
Maybe we can.
So shall I leave
personally? Yeah.
No, let me just unshare. I don't know how to. Okay, but anyway, so I think I'll just leave when you guys are done.
Yeah, you can just leave. Yeah.
Okay. Thank you very much. Thank you for the questions, etc.
Yeah.
Yeah. Bye.